Alrighty, Project 3, Analyzing the Spring Mass Characteristics of Vehicle Suspension, specifically in NASCARs. We're going to be designing some of our own racing shocks. In Part A, first thing we're going to do is we're going to build some of our equations. We're going to take a generic second-order differential equation, and we're going to convert it into two first-order linear differential equations, and then throw that into a matrix. And then we're going to manipulate it by changing the B variable, which is essentially the density of the shock fluid inside the shocks themselves, and see what that does. And then in Part B, we're going to go and take a look at the elastic limits of non-linear springs. Man, I can't talk today. And essentially, that's going to look at if a spring is pulled too far and it can't retract all the way, or pushed too far in, what will happen there? We don't know yet. Let's start off with a standard form of a differential equation for a mass spring system. Over here on the left, we have m, mass, times the second derivative plus b, the variable I will decide later, times the first derivative plus k, the spring constant, times x equals 0. And this is just rewritten it with our variables that we already know. Now we need to convert the second order differential equation into two first order differential equations. So essentially we can use properties of physics to rename a couple variables here. We're going to name x1 as position. We're going to name x2 as velocity, which is the derivative of position, and then acceleration as the derivative of velocity. Now we need to make a linear system. So, well, we already just said the derivative of position equaled the velocity right here. So I just rewrote this with a 0 in the spot here as the coefficient for position. That way it makes more sense linearly when you throw it into a matrix as a first equation. So, but the second equation is a little bit more tricky. I pulled it down, and we have 175. This here is acceleration, which is the derivative of velocity, plus b times velocity, plus this times position equals 0. And I just swapped these in for what was here, right? This is the second derivative, this is the first derivative, this is the variable. And then I'm going to rearrange the whole equation to solve for the change in velocity, which is the second derivative. Okay, so I rearranged the equation. Here's my change in velocity equal to this minus that. But actually, these are literally just coefficients in front of x1 and x2, which is the same thing we have up here. So if we rearrange this again, we get x1, x2, x1, x2. Oh, look at that. Now we have two equations that we can throw into a matrix. Oh, there we go. That looks familiar. Now we're getting somewhere. We formed a matrix here. We have our change in position and our change in velocity here equals the matrix itself. This, by the way, is a B because we're going to change that later. And then we have x1 and x2, right? Because you can factor them out using properties of matrices. And now let's take a look. I actually just threw it all into Excel, so I didn't want to do it all by hand a billion times. Alrighty, now we're in the second section of Part 1, or Part A, and we're going to go through 6 different scenarios for B. We're going to go through the significantly overdamped, slightly overdamped, critically damped, slightly underdamped, significantly underdamped, and then the last one is undamped, where there's it bounces forever. We already know that, so I'm not quite sure why we're doing it, but I guess we could look at the chart anyway. Okay, so the first section here, and I put all these into Excel, by the way, with the matrices to solve for the eigenvalues and everything. I don't know why I bothered doing that, though, because turns out all the eigenvalues are actually equal to the R values, except for scenario 3. The only exception here is there's only one R value. Scenario 3 is the critically damped scenario where B is equal to 4 times M times K, which essentially means that you're adding or subtracting the square root of 0, which is 0. So you only get one answer because if you add or subtract 0, it's the same thing. And then everything everything overdamped is real. Everything underdamped is imaginary. It generates an imaginary number, of course, because B is less than the negative M times K times 4. Yeah. So I'm not sure what the point. I don't really know why we're doing the eigenvalues. I didn't find that useful in this project, but that's just all the information about them all in one slide, because there's nothing really more to say about it in the rest of the presentation. So there you go. Take a look at this here graph. This green line represents an arbitrary spot. I happen to click on the graph. The reason why it's here is because it's the same starting point in every single graph for the rest of this section. So it shows the change between each graph for each B value. It's just a reference point. It really doesn't do anything other than that. But I think it's actually wrong here, because if you look at the arrows, they're all going down and then this is going up. I don't really know what's going on here. I was expecting it to do something like this based on how the arrows are behaving, because it's doing something like this in the rest of them, in the rest of the scenarios. For instance, if we take a look at this scenario, when B is slightly overdamped instead of significantly overdamped, it follows a similar trajectory as to what I was expecting the significantly overdamped curve to follow. But I don't know. It's the same starting condition, or initial condition. So I think it's probably an error in Bluffton, I believe is how you pronounced it. Interestingly enough, the playing fields for scenario 2, 3, and 4 are all exactly the same. They all look exactly like this, probably because the B values here are so close together. I mean, because we're trying to do critically versus slightly, so it is slightly overdamped and underdamped, very slightly, resulting in very similar graphs. Here, though, is significantly underdamped, and the curve is different. Instead of more of a gradual curve, it goes down, curve, and then a straight line, a seemingly straight line here, instead of a gradual curve that we've seen before. Oh yeah, the nearly undamped, it basically bounces forever. Cool. You don't want to ride a car with this because the suspension has no limiter, in a sense, where the spring's just gonna go like this the whole time you're driving. Every move you make, I mean, it eventually will wear out just because energy loss, right? But I mean, when you're driving a car, you're constantly hitting small bumps in the road, and it's just going to keep shaking up and down. It's going to be a miserable ride quality. You don't want an undamped spring. Okay, yeah, so the pros and cons, kind of to cap off section A. The Goldilocks method, undamped, is obviously way too bouncy. You don't want that. We just talked about it. Overdamped, significantly overdamped, is way too stiff for a NASCAR. You're going to kind of want something really close to critically damped. You could go, I mean, just a hair slightly overdamped or slightly slightly underdamped for a NASCAR. But critically damped is pretty good as a balance. For passenger cars, like for daily commuters, whatever, you're going to want something a little underdamped because of all the bumps you're hitting in the road. But because NASCAR tracks are generally flat, you're going to want critically damped. Okay, now we're moving on to part B, where we're focusing on non-linear springs, or soft springs. They essentially have built-in limiters. I didn't even know there was a difference until this project, so that was kind of neat, I suppose. a difference between linear and nonlinear springs. We're particularly curious here about the critically damped scenario, since that is the one that's optimal for the NASCAR. So that's the one we're going to focus on in part B. What we're changing here is we're changing this section here in the middle of the equation, where we just had x here before, but we're subtracting a constant times x cubed from x. So of course, if the constant is 0, no change, right? But once we start once we start increasing the constant, then we're going to see this whole equation change. So let's see what that looks like. Yeah, exactly. When s is 0, it's going to literally equal the exact same thing it did before. But with an s value of 1, it's going to completely flip it, apparently. I was not expecting this to happen so early. I was thinking, oh, maybe when s is 1,000, right, something will change. No, literally, if you make... Oh, I forgot to mention. It's C, because if you put S here, it's already a predefined constant in Bluffton. So everything turns red and it crashed the web page. Yeah, so I had to use C, just so you know. Anyway, I was talking about how these are all going straight up. And this is pretty zoomed out too. It's zoomed out all the way to 4,000. You have to zoom in a little bit here. There we go. If you zoom in and you change this all the way down, I mean, that's like 7 decimal places you have to go down. That's so small in order to get something that's a nice arcing curve. What essentially this curve means here is that if you're under 1,000, right, because 6, 8, and 1,000, I guess it's behind my screen, sorry about that. If you're under 1,000, it's going to converge back to 0, right? You get this arcing curve. Here's the issue. If you're above 1,000, though, it's just going to go off into infinity. It just goes straight over there, right? Well, the conclusion I can draw from that is I don't know the units, because there are no units given for B or for anything here, except, I guess, kilograms is one of the constants. Anyway, there aren't any units given, so whatever 1,000 means, if you go above 1,000, let's say your limit on your spring is 1,000 something or others on your car, and you exceed that, your spring breaks, right? And then it just goes straight off into infinity. That's essentially what I understand that to mean. Oh yeah, I guess that's all I have for this project. A couple wrapping up thoughts. I did not find this project to be enjoyable because there wasn't like an objective I'm trying to prove. I really liked the project where we went over those Wheatstone Bridge examples and tried to solve them, because it was something that we could actually solve and be like, oh, this is how I use my math. And then there was a second part of that where we like applied it to a part of history or something in the real world as a circuit example. But this project seemed kind of useless because I literally just have to look up the definition of undamped, overdamped, and underdamped, and critically damped to know how my NASCAR should be. That's all I had to do. I didn't have to do any of the math because it didn't really show, it didn't prove anything. So yeah, maybe I missed the point, but there was no objective listed in the project. So yeah, I was kind of disappointed and a little bit confused, but I guess it turned out okay. And part B was a little bit more interesting because I never knew there was a difference between linear and nonlinear. So that was pretty neat. But anyway, thanks for watching.